Welcome to another design review video. In this video, thanks to Pietro for sending in his board, we're going to be looking at a Xilinx Spartan 7 mini board, and he's intended to be this kind of his first FPGA design board in Altium as a sort of breakout board powered by USB-C with a simple JTAG programming interface. This is the first time I'm looking at this board and also the schematic, so we'll go through the things I pick up on immediately, what Pietro has done well, what maybe could be improved on, as usual in these design videos. If you'd like to submit your own design for review, please go to fils-lab.net/contact, fill in the contact form, or send me an email at phil@fils-lab.net. Please send me a link to your GitHub profile or to a WeTransfer upload, and don't send me your files directly. Thank you also for Altium for sponsoring this video. Pietro did his design in Altium Designer, so I'm going to be showing you around a bit there as well. If you'd like to give Altium Designer a try for yourself, you can go to altium.com/yt/philslab. I'll also leave a link in the description below to get yourself an Altium Designer free trial. Speaking of design reviews, and also speaking of Altium Designer, there's currently a PCB design review competition run by Altium, showcasing one of my PCB designs, and I've added a couple of mistakes there for you to find. So you can inspect the design, find at least one mistake I've put into this design, and get a chance to win a $200 gift card. I'll leave a link to this in the description below as usual. Back in Altium Designer, let's have a brief look at the project overview. On the right hand side in the projects panel, we can see various schematic documents, as well as one PCB document. The first thing I notice is that the schematic document doesn't have an overview, so there's no overall block diagram or connection diagram, which I would want for a board at least of this kind of scale with many different schematic pages. Secondly, also the schematic documents aren't organized. We start off with flash and RAM, then we jump over to power supply on page 2, then headers, and then some FPGA. So it's not entirely organized, and that's something I would like to see in a slightly larger design like this. In any case, let's go through 1 to 6 of these schematic pages and then finally look at the PCB design. Again, this is the first time I'm looking at this, so these are things that are immediately jumping out at me. Here we are on the first page labeled Flash and RAM. I like that Pietro has given it a title at the top here, and then also subsection of the schematic giving us an indication of the Flash and RAM sizes, for example. I immediately noticed that the title block hasn't been filled in, and I understand this board is still in progress, but before moving on to PCB design, I would like to have my schematics clean and somewhat finished, so that's why I would like to see that here. The first gripe I usually have is, instead of using 4.7K, I'd like to say 4K7, because this little dot could get lost, so to speak, when printing these schematics, and so forth. So this makes it clearer to me. On the other side, we see this 100 nanofarad capacitor. Again, these are small things I'm picking up on at the moment, and we'll go through as well. Nanofarads, farad is pretty clear that a capacitor will be in farads, so we can omit the F. We also omitted the ohms in the resistor. It doesn't say 4.7 kilo ohms here, so why put the farad behind a capacitor? It's pretty clear that it's in farads. Another thing I see is odd labeling of the components. I assume Pietro has done the automatic schematic symbol annotation, which means on the left side we start with U2 because this component is placed lower than U1, but I would want my flow generally to be left to right. So this should be U1 on the left here, this IC, and on the right side this should be U2. Same goes with the capacitors and resistors. Flow from left to right, top to bottom, and so on. Other than that, it looks pretty clean. I like that the grounds are pointing down, the 3.3 volts are pointing up. Again, 3.3 volts, I'd rather have that this label is plus 3V3. Same reasoning as for the resistor or capacitors or anything else. I like that Pietro has added this schematic blanket, that we can use this net class to do, for example, length tuning and so on. So we have a bit of flash memory, a bit of DRAM here, which will then interface with the FPGA. The flash, of course, used to store the program memory, and DRAM for some volatile memory. Going to page 2, and ideally, after an overview page, my power supply is usually one of my first schematic pages, so I can see where do my voltage rails come from. If we start with page 1 as a schematic and see 3.3 volts, for example, we don't know where this is coming from. By having a power supply page first, we can immediately see we have an input voltage, which happens to be this Type C USB connector, and that's giving us 5 volts nominally through a filter, and that then feeds this triple buck converter. Looking at the USB-C connectors, we're only using this for power, therefore we have pull-down resistors of 5.1 kilo ohms. I'm not sure why Pietro is going with 5.11, 5.1 is a perfectly fine value. However, we're missing net labels. So if we go to the PCB design later on, we'll see that this net is not labeled, for example, USB-CC1, and this one isn't labeled USB-CC2, but rather these will have names such as net J1, pin A5 or something. I strongly encourage labeling absolutely every single net. Another thing I would like to see is moving this pi filter up here and then connecting it directly. This just makes it clear rather than having to jump around the schematic. We come from VCC, from our USB-C connector, through this pi filter, and that generates our 5 volts, so to speak. There's no reason for having these separate. For FPGAs, we typically want a power sequence, and that's the reason we have these separate enable signals here as well. However, Pietro has just hooked them up with 0 ohm resistors, so effectively shorts, straight to the 5 volt or input voltage rail, which means all of these output voltages, 1.0 volts, 1.8 volts, and 3.3 volts, will turn on all at the same time. Now, while this will probably work for the FPGA, the datasheet recommends, or application notes recommend, that we should power sequence these. For example, might be starting with a core voltage, then the auxiliary voltage, and then, for example, the remaining bank voltages. And you can feed the output voltages, or if we have various power good signals, to these enable signals to sequence our startup, and this is what I'd strongly encourage doing. At a first glance, the rest of these connections, at least on the left side of the switching converter, look pretty much fine. We have various mode select pins, power good, which is typically open drain, so we need a pull-up. However, this pull-up seems rather weak at 470 kilo ohms. I'd probably just use one of these 5.1K resistors, and this also reduces the size of my bill of materials. I don't want to have all these different resistor values, especially for your fairly unimportant pull-ups. So power good doesn't need very specific value resistor, so a 5K resistor is probably fine here. And this reduces the length of our BOM, reduces the length of unique entries, and thus reduces the cost or complexity of producing this board. Looking on the right side, we have our LC networks, 2.2 microhenries each, and our output capacitors, 22 microfarads each. Typically, for the smaller voltages, we might need more capacitance, and that's something I would have to check with the datasheet. So definitely double check if the LC values are correct, but typically the inductors will be the same for these FPGA triple or quad buck converters, but the output capacitance might change a bit. We also have our feedback dividers, so depending on whatever the feedback voltage here, this reference will be compared to this divider voltage, and that sets the output voltage. I won't go through checking, but of course it makes sense to go through and check these before you submit your design. I would like to have seen calculations for each of these supply rails just to give the design reviewer an easier job, so to speak, and also for yourself to verify clarity. One thing I can immediately see that is wrong is this 20 picofarad capacitor to ground. This is clearly wrong because 20 picofarads isn't a lot of capacitance, and it's in parallel with 22 microfarads the way it's shown here. This is actually a compensation capacitor and needs to be connected to the feedback compensation network. This is to change the loop response of this whole feedback network. This 20 picofarads has no use in decoupling or bypassing, it's changing the frequency response characteristics of the feedback system. Same goes here, this is a compensation network capacitor. We can of course easily see that if we just take a look at the first page of the relevant datasheet. This is between that switch node output after the inductor to the feedback node. And same thing for this connection here, should be something like this, for example. Also, the feedback nodes aren't labeled, aren't given net names, so that's something I'd change. Also, just saw down here the power out sequence Pietro has actually put down, but not then actually implemented. Another thing that we'd need to check is that this triple buck converter can actually supply the current this FPGA needs. Going to the third page, and something like this I'd probably put as one of my final schematic pages. These are just general GPIO headers, as well as the JTAG interface, some LEDs. So I'd either put these directly on the bank pages, or as a separate page towards the end. Because right now we don't know what IO34L7N or something is. I know it's got something to do with FPGA, but we haven't even seen the FPGA yet. So logically it would make sense to put the schematic page later on. In any case, ground should always be pointing down, in my view. There's enough space to do so. Even with this, we can just extend this out a bit and point that down, for example, like so. Depending on how Pietro will have routed these later on, these can actually form differential pairs, so you might want to put in a differential pair directive, pressing P, V, and then F, and then making these into differential pairs, for example. Again, it depends if you want to use them as single-ended signals, single-ended GPIOs, or differential. On the right side, we're using a JTAG header, power, ground, and the 4 JTAG signals. That looks okay. Of course, you'd have to verify the pinout with whatever debugger you're using. Then we have LEDs, again using different value resistors. We have 2K, we have 2Ks here, even though for this LED, for example, the power good, we use a 330 ohm. So why are we suddenly using far higher value resistors? We'll have dimmer LEDs in comparison to the power good LED, and we want to perform BOM consolidation as usual. So I'll just make them 330 ohms, all of them. I know different color LEDs will have different forward voltages, but approximately they should have similar brightnesses even if you use the same value resistors. I like that the mounting holes are displayed here as well. I think that's good practice. So finally, now we can move on to the FPGA part of the schematic. Let's look at the power section first. This looks like it's a Spartan 725 package, so a fairly small package FPGA, 196 pins. With all the ground pin connection, internal voltages, auxiliary and VRAM. We can go to the Spartan 7 FPGA datasheet, specifically the one talking about DC and AC switching characteristics, to see what supply voltages we need. These are the maximum absolute ratings, but from that we can quickly get, okay, it's about 1 volt for VCC int, VCC aux will be about 1.8 volts, and VCC VRAM is 1.0 volts, and bank voltages around 3.3 volts. So this looks pretty much correct to me. I assume the decoupling caps Pietro has gotten from the relevant datasheet as well. On the left side, this looks good. We have the largest value decoupling capacitors placed furthest away, and this corresponds also to the PCB layout that we want smaller capacitors, higher frequency capacitors, close to the IC. And we can also symbolize this in the schematic. Whereas on the right side, we have the 100 microfarad closest. So I would like to take this and just flip this around, just to make it clear 470 nanofarads closer, then the 4.7, and then the 100 microfarads. Also, we have these 4 wire nodes here, and generally it's hard to see if things are connected properly. So that's why I maximum have 3 wires coming into a single node. And I've explained this before in several other videos. Other than that, this looks okay. Then moving on to the banks, this is a fairly small FPGA. We're not connecting any DDR memory. We're connecting some flash and some DRAM. So we don't have too much to worry about with the pins. We have a 100 MHz crystal oscillator, decoupled with a 100 nanofarad capacitor, the output at pin 3. Going back to page 1, we see that the clock connection of the SPI memory has a 100 ohm resistor to reduce ringing. I didn't mention it in the first page, but this should be placed at the output of the FPGA, because the FPGA will be the master driving the clock, and therefore will be the transmitter of the clock, and we want to place the resistor at the transmitter, so the FPGA. So ideally I want this 100 ohm resistor at the FPGA side. Anyway, the reason I bring that up is because we might as well place this 100 ohm resistor or 0 ohm resistor at the output of this oscillator, again for the same reason, because we might want to slow down the edge rates, we can reduce ringing and so forth if we need to. This 100 MHz clock pin, however, feeds L5, which doesn't seem to me like it's a clocking capable pin. I would have to check the datasheet, but there's a reason why we have SRCC and MRCC pins. SRCC is single region capable clocking pin, and MRCC is multiple region capable clocking pin. I would tie my clock output to an MRCC pin because this means I can feed the majority of this FPGA. I'm not sure even if we can use IO25_34 up here as a clocking input. So I believe that would have to be changed to an MRCC or an SRCC pin. Other than that, I would have to verify the pin connections for the DRAM, but of course FPGAs are pretty flexible, as well as the FPGA flash memory interface. Again, looking at the schematic symbol, we see MOSI and DIN, so some of these pins look like they're probably right as well. Other than that, I like that Pietro's used blankets and net class names because this will make the routing life a bit easier as well. Jumping over to the final page, we have the FPGA configuration. We're not using the battery, so we can tie that to ground, either via 0 ohm resistor or directly. We have various done pins, init B, and mode configuration pins, and I assume and I hope these are right. Again, bomb consolidation, we're now using a 4.99 kilo ohm resistor here, and we used a 5.1 kilo ohm resistor previously. We can probably get away with using a 5.1 kilo ohm resistors here and here as well. I know Xilinx usually recommends keeping these resistors or pull up and pull down resistors about 4.7 kilo ohms or less, but we can probably get away with this here. So bomb consolidation again, don't use so many different resistor values if you don't need to. Same goes with a farad bead. We are using 600 ohms at 100 megahertz. However, the power supply, we use a different one as well. Again, just increasing the size of the bill of materials. We can check that by going to reports at the top, bill of materials, and we can see we have a 39 row bill of materials for such a small board. A lot of them because we have so many different value resistors and also very many different capacitors. Other than that, we can of course clean up the schematic a bit more. There's no reason why this needs to be this high. But as you can see, something's weird with the grid as well. This grid is currently on 25 mils, and I saw Pietro's using my libraries for these parts as well. I've designed the libraries so they fit on a 100 mil grid. So everything is tailored to 100 mil. If we zoom in, however, we can see there's a lot of stuff that's actually off grid. Although this works if the connections are made properly, this makes editing the schematics, changing the schematics, adding new symbols very, very tedious because everything's kind of off grid. So you see, as soon as I try to move something, it snaps to the proper grid. And then we get all of these off grid items. And this is generally pretty bad practice. It makes editing schematics really annoying. It makes creating schematic symbols really odd as well. So it's fine if you do it for your own library, stick to one grid. Using the manufacturer part search in Altium Designer, all these parts are made for 100mm grid, and I believe that's pretty much the standard for Altium Designer. Correct me if I'm wrong. So I'd like to see everything placed on 100mm grid. Just a last note about schematic annotation as well. For a multi-page schematic, where I have page 1, 2, 3, 4, and so on, I would like to start my schematic numbering in order of hundreds. So on page 1, I'd use U100 as the first IC, then U101 as the next. On page 2, I would then use U200 to start with, same for capacitors, inductors, and so on. This makes it really easy then to go between PCB layout and schematic. If I'm looking at the power supply section, everything here will start, for example, hundreds or 200s, and then I can easily jump to that schematic page. Also saw some of these items aren't annotated properly. For example, this part of the FPGA is just UA. This FPGA doesn't even have a number, so that's missing as well. In any case, it really pays to make clean schematics. In any case, that's the schematic pretty much done. We can move over to the board. Alright, let's move over to the PCB design aspect after having looked at the schematic. This is a double-sided assembly board with majority of the main ICs on the top, and of course some passers, decoupling and so forth on the bottom side. Again, this is in no particular order, but let me just go through what I see instantly. First thing is, if I press 2, I can go to 2D layer view. On the bottom side, we can see the layers we have. This will be a 6-layer board. However, the layers aren't labeled properly. We have top layer, then suddenly layer 1, layer 2, layer 3, layer 4, layer 6. This gives me no indication what these layers actually do. The way I label my layers is I'll say layer 1, for example, and then I'll say in brackets, this is a signal layer. Then layer 2 should usually pretty much always be ground, so I'll type in layer 2, ground, and so on. This gives me an instant indication without me having to jump through and seeing what every single layer does. So let me just change that briefly, just to make my life just a bit easier. So I've now changed the names of these layers, and for those of you who know my channel and have been watching a bit longer, you see there's something pretty wrong with this stack up. It starts off well, we have signal of course, then we have ground, then we have signal, but then layers 4 and 5 are flipped. Layer 4 should be power, and layer 5 should be ground. Remember, adjacent to any signal and power layer, we want at least one ground layer. So what happens with this signal layer here? It has a power layer next to it. However, this power layer, in theory, that might be fine if it's a continuous power plane, has splits in it. We'll see in a second that Pietro is actually taking care of this. However, it's not good practice to have a power layer directly under, for example, the bottom signal layer. Pietro has taken care of it in the sense that he hasn't routed over the splits, at least tried not to. So you can see here all his routing on the bottom layer, which is the dark blue, is not done over any splits, which is good, but still I would not encourage this kind of stack up. I would want to have layers 4 and 5 flipped. It's pretty easy to change these layers. We can just move layer 4 to layer 5 and layer 5 to layer 4, and we get the same result, except we now have a better stack up. Also on layer 3, which is our strip line, or one of our strip line layers, Pietro hasn't routed very much, and also these signals are fairly low speed, SPI, JTAG, and so on, and that's fine just having one reference plane. They don't have to be strictly routed as proper strip line. So that's the first thing I would change. Let's go to design and then layer stack manager. We can see Pietro's nicely set up the layer stack, so for this 6-layer board, he's typed in the various cores and dielectrics. Even though this core seems rather thin in the middle, I assume that's probably a pre-preg. Type in dielectric constants, let's check the impedances, and we have impedance as well. So single N and 50, and we have differential. One of the first things I saw as well, first of all, the net names aren't there, which makes this net L1 underscore 1 or net R9 underscore 1, net R8. Makes it confusing. What do these nets mean? What do they do? And this is why I strongly encourage net names. I know it might take longer, but it makes your routing life and other people checking this design much, much easier. So please label your nets. The next thing I see, again, sorry for the random order, is these tiny, tiny clearances. So we have a 5-volt polygon pore here, yet we have, if I use the measure tool, 0.03 millimeters. So not manufacturable or door, which makes you check, have the design rules been set up properly? So go to design, rules, and we can see Pietro has used a minimum clearance for absolutely everything of 0.03 millimeters. You typically have to pay extra to have even clearances of 0.1 millimeters, so he's done a third of that. I know this makes your routing life easier, seemingly, but this is very bad practice. The way to set up your design rules, and they're there for a reason, is to stay away from minimum manufacturer capabilities. So I'll look at my manufacturer capabilities, type them here, and add in a small margin. So I'll even try to stay away from the minimum manufacturer clearances without a cost adder. Of course, given that my design can be routed and laid out that way. So my minimum clearance I'd probably set to 0.2 millimeters and then adjust them, because for through holes you'll have different clearances than for vias or copper and pads and so on. So definitely don't just type in a 0 millimeter clearance or anything like that. If I do a design rule check here, I'll have loads of errors now because this wasn't routed properly from the get-go. You need to set your design rules up properly first. You can't just route thinking you can do 0 millimeter clearances or 0.03 millimeter clearances. Basically, given that, you'd probably have to reroute much of this design because you've been routing it based on impossible clearances, impossible track widths, and so on. The next thing I see looking at this power section is these very sharp-edged polygon pores. Also, looking here, we have these split-up polygon pores. There's no reason why I can't just make a single polygon pore. Pressing P and then G, I could make a single polygon pore like so. Right, there's no reason they have to be split up. I don't understand why there's a reason to make two separate polygon pores, which is overlapping. It means you have more polygon pores in the polygon manager, and it's not very clean. Secondly, not only do I think completely square polygon pores don't look very nice, but there's also a problem with square corners, for power systems at least, is that you have higher current densities at sharp edges. That's why I like to round off my corners, or at least do 45-degree corners, so to speak, for my polygon pores. Additionally, you might want to think about thermal release, going to connectors or smaller parts, making sure there's copper balance on each side of the component. For example, these small resistors here, 0402, they've got a fairly sizable copper pore on one side and thin traces on the other. So there's going to be a thermal imbalance. You might get problems with soldering. Another thing again is the clearances. So clearances between this 5-volt pore here and the switch node pore here is pretty much non-existent. Then we have only 2 thermal vias underneath the switching converter, and for FPGAs, of course, you need several amps, typically of current at various voltages, and I don't think just these 2 vias will be enough for thermal dissipation. Also, they're placed pretty much central to the pad and not around the perimeter, and depending on your solder placement, these will be sucking the solder away. So more thermal vias placed slightly differently. Again, sorry for the rather jumpiness and the random order, but looking at the vias size on the right side, we have a diameter of 0.4 millimeters and a hole size of 0.2 millimeters. For this design, also given that the FPGA, which we'll see in just a second, has a very, very wide spacing of 1 millimeter each side, we can get away with much larger vias. Let me take one of these vias, put it in the middle, just as an example how large this via can be. Even with the 0.6 millimeter via to this pad, we still have about 0.18, almost 0.2 millimeters clearance to each of these pads. So there's no reason to use these small vias, which again are cost adder in this design. We could use somewhat larger vias, maybe 0.25 millimeter holes and so on, which typically don't cost more. Also, the annular ring for these vias is very small, so 0.2 millimeters and 0.4 millimeters, the annular ring is about 0.1 millimeters, so right at the edge. Definitely make the pad at least bigger if you're not going to increase the drill size, so maybe something like 0.5. Also clearance, spacing, you have the space, use it, so space these vias further apart. Also, just in terms of layout and placement, this isn't particularly clean. We have items not placed on grids properly, we have this inductor slightly more to the right than this one, this inductor doing kind of its own thing over here, and we have large loop areas. We're going from the switch node output here via this inductor to the output capacitor, and the output capacitor's ground is somewhere up here. If we use the measure tool, we have this whole loop we have to traverse, and the golden rule of laying out switching converters is keep your loops small. So a better way of laying this out, I'll be having the inductor like so, and the output capacitor like this. We've already significantly decreased the size of the loop. A better way of doing this is moving these resistors to the back side, which gives us a bit more space, and then we could move the capacitor down like so. Even better. We want to prioritize our switching nodes, our power loops. All these passive components, for example again, net R9 doesn't tell me anything. I assume this is some sort of mode select pin. We can place this on the bottom side, no problem. And ideally, if you can, try and ensure some sort of symmetry in your design. On the bottom side, it seems like we have our feedback networks. And I didn't see from the schematic, but these are actually 0201 size resistors, which are tiny. There's no reason for using those. We have enough space on this whole board to pretty much use 0402 size parts. Probably also for the decoupling capacitors, which we'll see later on as well. So make these larger, space these feedback networks further apart. Again, these are sensitive traces, sensitive parts. They're also pretty close to each other, which I wouldn't do, because we then get these very small solder mask slivers, which aren't really manufacturable. So proper spacing, proper clearances, and so on. It's good, however, that these are placed, for example, on the opposite side, away from the inductor, so that's something I'd probably do as well. Also, when it comes to ground and via and power connections, you see Pietro's use Y traces, which is good, but the ground vias are pretty far away from the pads, so I'd definitely like to see that moved in, for example, like so, or at a stretch, something like this. So make your ground and power connections as short and wide as you can. Of course, the via not too close, because you get problems with soldering. The via will suck solder away or wick it away. Same thing for these connections up here. Try and move that a bit closer in. Again, sorry for the rather jumpy and random order. We have this ground port up here, but I guess Pietro is more used to KiCad, where KiCad for an arbitrary power port will fit it to your board outline. This is not the case in Altium Designer unless you use a plane layer. For this, there's two problems. One is that we get this extension of copper going above outside of the board edge. In a 3D view, we can see that here. The board outline is here, but the actual copper is extending out, so that's not right. Additionally, regardless of any copper, if it's a plane, if it's a trace, you need clearance from the board edge. Right here, the board edge is in line with the copper. We need to move that down at least, I would say, 0.25 millimeters and give ourselves some clearance between the board edge and the copper. Also, this copper pour is rather arbitrary. I'd like to see a copper fill in these areas as well if you are going to pour copper. And we're also missing stitching vias. So between these ground planes here and the top and bottom copper if we're using ground, for example. We also have mounting holes in this design, for example here. And if you have a mounting hole, this doesn't seem to have a pad. So we can see this mounting hole isn't set up correctly. We have a hole size of 3.2, but a pad size that is actually smaller. Either you make the pad size the same and have a non-plated hole, so I deselect this option, or you have a plated hole with a pad size that is, of course, larger. So, for example, 5 and 5 might work for this design. Then I would, of course, get rid of the Silkscreen here, but this means you could have, for example, grounded mounting holes, which might be helpful in certain situations. If you want mounting holes which aren't plated, I would make the hole and pad size the same, get rid of the plating, and then make also a cutout of the polygon pour here, so a keep out area. This means that, for example, if you screw a screw down and it breaks through the solder mask, we don't get a short, for example. So I'd like to keep a clearance around my mounting holes, depending on the situation, of course. Next, let's look at the FPGA layout after we've done the power and so on, the polygon pours and so forth. At least when it comes to power layout, what I like to see is something like this. So I have my power and ground pins, and they usually come as pairs in FPGAs. I'll route them out with Y traces, via down to the bottom side, try to keep my via spacing as close as I can on the bottom side, and then connect capacitors up like so. So I think that's pretty good. That's how I would do it as well. However, sometimes I'm missing some ground vias. There might be components underneath. For example, here there aren't, so there's no reason why we can't put another via going down here. Ideally, if I can, for every ground and for every power pad, I want one via. Of course, in some very dense designs, this isn't possible. For something like this, per ground and per power pad, I want one via. Then on the bottom side, the decoupling looks okay to me. We can probably get away with using larger parts. We don't really have to use these 0201s because we have plenty of space and we're not fanning out very much of this generally pretty small FPGA anyway. Because we have multiple grounds, so we have layer 2 ground, layer 4 ground, every time we route down with a via, change our signal layer, we're also changing reference layers. I've explained this in several other videos, for example, my video on vias. Every time you place a signal via, you should also have a transfer via, which is a ground via, close to it as well. I'm, of course, not taking care if there's any signals underneath, but you should place a ground via close to any transition signal via. And this makes sure we have a return path also when we're going along the board in the Z axis. So these seem to be missing here, and we have plenty of space to do that as well. Next, when it comes to routing these differential pairs, we've added length matching between the differential pairs. If that's needed, depends on the design. But also, the spacing between these meanders is far too small. Just because it's the same signal doesn't mean you can't get coupling between itself as well. So I'd like to increase the spacing, for example, like so. Spacing of at least 0.4, 0.5 millimeters. Of course, that means you'll have to have more meanders if you want to match all these signals between each other, but this is very, very close spacing, so you're going to get a coupling within itself. Also, if you're matching interpair skew within a differential pair like Pietro is trying to do here, you should do it next to discontinuity. Discontinuity might be an entrance in or exit from a pad. For example, up here, I'd rather place my intra-pair skew matching, but also this is a very, very large excursion. I'd rather make my excursion smaller and then have two of them. to make sure my impedance isn't affected by too much. Also, the coupling behavior isn't affected too much, rather than having this very large excursion here. So I prefer to do something like this, matching the skew, and then place it closer to a discontinuity anyway. Again, with regards to clearance, we should move these away from any through holes specifically. For example, something like so, and then we also have to move this polygon pore away as well. Keep in mind that, of course, any polygon pore close to a trace will change the impedance behavior of that trace because we get coupling. If we look at the strip line traces on layer 3, we can see we have some JTAG signals routed here, and again very close to vias and very close to each other. There's no reason for this trace, for example. Why don't we just route below, like so? This gives us clearance, this gives us spacing between the vias, and we can just generally space out our traces even more. If you have the space, again, use it, right? There's no reason why we have to be so huggy with the traces the whole time. Like so, and we've immediately improved the routing of this, staying away from traces, polygon pores, any other components which aren't part of the signal. Again, this polygon pore seems very arbitrary to me. We could fill in the copper inside here as well. We're getting some weird imbalances in terms of copper, and we're again missing the stitching vias. Looking at the power layer in the center, this is our power distribution to the FPGA and memories and so on. We have these seemingly weird copper patches. I don't know if these are supposed to be keep outs or something, but we have these random disconnects of copper, and these seem to be underneath the inductors. And I'm not sure why that is, if it was part of the footprint, but there's no reason for doing that. Also, these are on layer 5, and the inductors are on layer 1, so it's further away anyway. There's no reason to have these weird little cutouts in the power planes. So there's quite a few things we can clean up and redo with this board. Let me just briefly talk through some smaller points as well. For example, the Silkscreen. Let's have a look at that on the top overlay layer. The font is rather small, 1.25 millimeters, and we have the space, so we can easily increase the font size here, 2 millimeters maybe, and even make that bold, for example. And this will make it easier to print and easier to see. 1.25 millimeters is rather small. Also, the labeling seems to be very sporadic, so it's not aligned on some grid again. We have things floating around, so I try to clean that up as well. Maybe add my initials, a name for the board, pin out of these connectors as well, and so forth. I know this video is probably getting rather long now, so I'm going to try and keep it short. I'm sorry if I couldn't cover everything with this board, but there's quite a few things I'd like to see changed before attempting another design review. Just looking at it now, I also see that this USB-C connector is far too inwards on this board outline. Remember, we have the USB-C plug, which needs to plug in, so we need some spacing and we need some overhang of this USB-C connector. So I'd probably like to have the USB-C connector something like this, which gives us plenty of space for the plug and still gives us clearance between the through-hole parts of this footprint and the board edge. Considering this is one of Pietro's first designs with an FPGA, I think it's a good start, probably better than I could have done with my first try. Thank you, Pietro, for sending in this board. I hope this very brief design review of some major parts in this design was useful, so thanks again for sending this in. So thank you very much for watching this video. I hope it was useful also for others to improve their designs. If you haven't already, please do like the video, comment if you have any questions, and do subscribe if you haven't either. On the topic of FPGAs and designs, I have some videos on FPGA designs, how I would do them. For example, there's FPGA and PCI Express hardware accelerated design, which in 30 minutes gives you the main points when it comes to FPGA boards. Thanks for watching, and I hope to see you in the next video. Bye bye.